Colorado, and Boulder. Dr. Rey is internationally recognized as a leading theoretical physicist.
This meeting is being recorded.
Theoretical physicist pushing the frontiers of science and technology at the intersection of atomic, molecular, and optical physics, quantum information science, and condensed matter physics. Dr. Rey's deep scientific insights and innovative fundamental methods to understand, control complex quantum many-body interactions and leverage unique atomic and molecular structure has had profound effects, shifting the paradigm of how the global community approaches quantum information science and quantum simulation, and inspiring and directly leading to record-breaking atomic clock performance and much more. Dr. Rey is further distinguished as the recipient of the MacArthur Foundation Fellowship, also known as the MacArthur Genius Award, and the Presidential Early Career Award for Scientists and Engineers. Dr. Rey is also an elected member of the National Academy of Sciences and a fellow of the American Physical Society. Without further ado, it is my great pleasure to present to you Dr. Ana María Rey.
Thank you, Grace, for the very, very kind introduction and for the opportunity to speak here today. Let me start by sharing my slides and let me see if you see them properly. Here, can you see them at the moment? Great, excellent. And then I'm going to have this 1 second, sorry. Okay. Oh, sorry, one. It was working great before. Hopefully, it's like slide look great. Yes, but can you see when I change the screen?
No, we can see the slide that you're on.
Yes, exactly. So then I think let me okay. It was working before. Let me share one more time. Let me put. Let me first do here.
That's fine. Take your time.
And okay, share my screen. Share. Now, can you see the screen? The slide that is changing?
Yes. Or no, we can see
Yes.
the main slide, and then when you go, you're fine. So you're good to go, ma'am.
Okay. So perfect. So let me try and see. Hopefully it's working. So sorry for the delay. It's just want to say that it's a great pleasure for me to speak here today. Really a big honor, and I hope that I can take this opportunity to tell you a story of a topic that I find that is very exciting and hopefully can lead to very interesting advances in quantum simulation and sensing. The topic that I want to discuss is long-lived multi-level atoms in cavities. So I hope that at the end of this talk, I can convince you that these are really fascinating systems. So with that, let me, can you see my slide? Hopefully, yes. So let me start to introduce the idea of ultracold atoms, because I know that maybe the audience is very diverse. So I just want to all us being in the same page. So by ultracold atoms, what first we have to realize is that when the temperature of the gas is a measure of the average kinetic energy of the atoms in the gas, and therefore if we are using a thermometer in order to characterize the temperature, we realize that at room temperature, that is the order of approximately 300 kelvins, we find that the atoms in the gas are moving extremely fast, almost at the speed of sound, and therefore it's very hard for us to control the atoms. Now, if you think about the coldest temperatures that naturally can exist in the universe, then you can think, okay, let's think about the temperature of the outer universe. And this is about a few Kelvin. And if you compare this temperature, the temperature of a gas, this is kind of the temperature at which helium condenses, that is of the order of 19 meters per second at this temperature where the atoms are moving, and therefore it's still very challenging to control a gas like that. So one of the biggest accomplishments that we have done in the last few years or decades is the possibility to cool down arrays of atoms. We can say the order of 10 to the 4, 10 to the 6 atoms to extremely cold temperatures of the order to 10 to 100 nanokelvin and very dilute, around 5 orders of magnitude more dilute than the density of the air. And at these conditions, the velocity of the atoms is just a few centimeters per second. And therefore, under these conditions, we are able to control and manipulate the atoms. Of course, this is an effort that has done by many scientists together. And for example, they were recognized by the Nobel Prize for these big accomplishments. Back in 1997, we had Steve Shook, Coin Tanucci, and Bill Phillips. They were able to cool down the gas using lasers to temperature of the order of microkelvin, and they received the Nobel Prize because of that. And later, Eric Cornell and Wolfram Ketterle and Carl Wyman, Eric and Carl from GILA, Wolfram from MRT, they were able to further cool down the atoms in the gas, like by thinking of the atoms as being as the coffee in a cup and letting the hot particles evaporate. This gives rise to the formation of what we call a Bose-Einstein condensate, that is a very new state of matter at very cold temperatures, and this led the scientists to be recognized with the Nobel Prize in 2001. So this is very exciting, but I mean, one of the questions that we want to understand is how we can use these very cold atoms for something useful. And the story that I'm going to tell you here is that we can use these systems to explore the quantum world. Basically, what we have is the opportunity for the first time close the very challenging gap between the understanding of the quantum behavior of few particles that we know how to control and manipulate into the complex but exciting and emerging behavior of many body systems that nevertheless we cannot describe very well or understand them. But the hope is that we can use these ultra-cold gases and the tools offered by atomic, molecular, and optical systems in order to bridge this gap. The idea is that with these ultra-cold systems, we have systems with very well understood microscopics that we can even write the Hamiltonian that describes the system is a piece of paper very cleanly and actually reproduce exactly what the system is as we want in the lab. Tune the interactions and the parameters of the Hamiltonian almost in real life during the experiment. And the system is so coherent that we can have access to quantum dynamics without the need, for example, of ultra-fast pulse or something complicated. It can happen during almost the time that the experiment is happening. So this opens really very important opportunities. And what I want to emphasize here is that this, in fact, can lead to advances that really could lead to important revolutions and technology. For example, in one case, we can use these fully controllable systems to build up artificial quantum materials that can feature behaviors that are more advanced than what we naturally find in the earth. So like natural materials, we can engineer them and actually try to emulate these behaviors and, for example, answer questions that we cannot answer now, or even go all the way from condensed matter to high energy. Moreover, we should be able to create sensors that are the best we have ever imagined, not only for time, but also for electric field, magnetic fields, accelerations, taking advantage of the quantum properties of these systems. Finally, we should be able to use these sensors and the control, for example, to shed light on fundamental physics, for example, the origin of the mysteries of the universe that we don't understand yet, like dark matter, physics beyond the standard model, the interplay between quantum mechanics and gravity, and that would be very exciting. And of course, the dream of creating quantum computers made by quantum mechanical elements that can harness entanglement, error corrections to build machines that with capabilities that we have not seen before. And we believe that atomic systems have the potential to shed light and contribute to all these directions that is really exciting. I believe that among ultracold atoms, one of the systems that have much more potential is what we call long-lived atoms. That is the topic of this talk, and I'm going to start explaining what we mean by long-lived. So we have many elements available to take advantage of, but the ones that we are in particular excited about are atoms that live in the second column of the periodic table, for example, the strontium, or other atoms that are in other parts of the periodic table, but share similar structure like atoms in the periodic table in the second column, like ytterbium. So what is characteristic of these atoms? These atoms are characterized, as you can imagine from the second column of the periodic table, that these atoms have two outer electrons. And the interesting part is that because of that, these atoms acquire a unique atomic structure that gives important opportunities for metrology. The idea is that we have the ground state, and then we have two excited states that are an optical transition, so very high frequency, but moreover, the transition from these states to this ground state is extremely long-lived. So we have the case, what we call the clock states, the 3p0 state, that has a transition that is both dipole and spin forbidden. Well, it doesn't matter. I mean, it's just the internal structure that gives this transition a lifetime that can be longer than 100 seconds. And we have other not so very long-lived, but still significantly long-lived, the 3p1 state that have a lifetime of 22 microseconds. What you can think is that these transitions are of the order of 10 to the 6 to 10 to the 9 longer than what you typically find in atomic systems. And because of that, because of this very long lifetime, this allows spectroscopic resolution, and that's why these atomic clocks have been developed using this very narrow transition. And in fact, one of the additional characteristics that I want to emphasize is that actually we are dealing not only with these very long-lived atoms, but with fermionic isotopes. And why fermionic isotopes? Because they have a nucleus that have also a finite number of Zeeman levels. So in the case of strontium, for example, the nuclear spin levels can be as large as 10, I is equal to 9.5. And for example, here in ytterbium, we have atoms, isotopes with I equal to 5.5, so 6 levels or 2 levels. And what I want to tell you today is a story that this multi-level structure can offer a playground not only for metrology, but also many body physics and hopefully even the development of quantum technologies. So now let me move a little bit and tell you one specific example. That is the case of this. Just making sure you are following all the slides that I'm talking about. Yes, everything is seen, correct?
Yes, we are.
Okay, perfect. So let me start now telling one particular story that I find interesting. If you think about the idea of materials and emerging behaviors, perhaps you cannot deny that one of the most exciting behaviors is the idea of superfluids or superconductors. These are materials that can conduct the electricity for a very, very long time without dissipation, and therefore they can lead to very important technological developments. And there are many aspects, nevertheless, that we don't understand about the systems. Just microscopically, this happens when fermionic particles like electrons are subject to very cold temperatures and in the presence of attractive interactions. In that case, these electrons tend to pair, forming what is called coupler pairs. And these coupler pairs can appear in the form of very weakly bound pairs or in the form of very tightly bound pairs that form molecules, because two fermions can form kind of an effective bosonic particle, a molecule, a composed particle. And in cold atoms, one of the biggest success was the idea that we can in fact see these superfluids using ultra-cold fermionic atoms. That was back in 2004 when the field started to develop. I think this is a picture of Debbie Jean, that she was a GLA researcher, that she pioneered the capability to cool down fermions made of fermionic particles that we can have a lot of control. And they have this very beautiful picture of a gas of either weakly bound pairs that is called the BCS. These are the dancers that are just dancing separately, but dancing still as pairs. And then the BEC, like, is these very tightly bound molecules where you have very nice couples just dancing almost together. And even though this is a story of colatons, condensed matter particles, the interesting part is the idea of having a crossover between these two regimes by tuning some parameter like the interactions. It's not only something that is believed to happen in materials, but also can have connections to high energy physics. For example, it's believed that after the Big Bang, we have a zoo of quark gluon plasma, very energetic particles, and these cool down and form the universe that we know at hand. But the idea is that if you try to understand the phase diagram of the system, then you find out that for low temperatures, then in some conditions, the quarks form these very weak bound pairs. In this case, the BCS phase is called color superconductor, because you can have different colors of quarks, and they can bind to form very composed objects that are the hadrons, the mesons that we form, we know that compose matter. So the idea is that in principle, trying to understand this transition could shed a lot of interesting understanding on various aspects of our universe. So the advantage is that this Hamiltonian can offer really a simple description in the terms of what is called BCS Hamiltonian. And this is written not in position space, but in momentum space. I'm a theorist, so I have to write a Hamiltonian. So let me try to introduce a little bit some equations, but very simple. So the idea is that at very cold temperatures, we have Cooper pairs that want to pair two pairs of electrons that form these compound objects, or empty sites. That is the only thing that composes the Hilbert space, because sites with only a single electron cost too much energy. So in this case, the Hamiltonian that describes the system conforms of an attractive interactions, and you can see the attractive interactions is the interactions that destroy a pair with momentum k and minus k and creates another pair with momentum k and minus k, and this is what favors the pairing. But in addition, well, we have the kinetic energy of the electrons, and they have the Fermi pressure that is characterized by a chemical potential that corresponds to the Fermi energy in the case of very low temperatures. So these are two competing terms, but and what gives rise to BCS superfluidity, to superconductivity. But years back, Anderson and Phil Anderson, the Nobel Prize winner, said that realized that this model can be even further simplified, because you can only have Cooper pairs of empty sites at a given momentum k, so you can reduce the Hilbert space instead to spin up and down particles. Spin up a Cooper pair, spin down an empty site, and therefore, instead of writing a complicated fermionic Hamiltonian, you can write the Hamiltonian in terms of spin operators that count if you have a spin up or a spin down, or flip one spin from down to up. That means destroy a Cooper pair or creates a Cooper pair here. And therefore, in this simple mapping, the Hamiltonian can be written in terms of spin operators. But the important part is that the interaction term not only can be written in terms of spin operators, moreover, they can be written in terms of collective spin operators. This collective is sum over the spin of all individual particles, and you have a collective S plus S minus Hamiltonian. I will explain a little bit more the physics behind, but I just want here to emphasize there is something that is collective, and moreover, the way that we characterize if there is a superconductivity or not is trying to characterize the coherences of the Cooper pairs that are characterized by the expectation value of this collective spin operator S minus. So when this is non-zero, then we have superconductivity. So then theorists were very excited about this possibility and tried to define not only ground state phases, but they wanted to speculate what happens if you do quenches, because our matrix is active. So what happens if you quench a system from the interaction from one value to the other, and try to look at the dynamics of this order parameter, or what happens with the properties of the system. So they were very excited that in fact, in this case, this system can admit some exact solutions, some complicated exact solution in terms of some what they call lax operators. It doesn't matter. They were able to predict what could be the dynamical behavior expected to have in this system. And they came up with a phase diagrams that depends on the initial gap or order parameter as a function of the final gap. So they have the initial and the final, and they said that depends on how you change the parameter, they can have different dynamical phases. They call it phase 1, phase 2, and phase 3. Phase 1 is the case when the superconducting parameter very quickly disappears on time, and therefore the system goes from a normal state to something that is from a superconducting state to something that is normal. The superconducting gap disappears. There is another case where you are going to quench and the superorder or superconducting order parameter is going to oscillate, but the oscillations are going to damp, and then every is going to start saturated at a given value of the order parameter that is finite. And then phase 3 is the case when the order parameter is going to continuously oscillate all forever. And I don't know if you have heard some idea of this time crystal that were proposed by time in Wilczek. They don't exist in equilibrium, but in principle, these time crystals or something that oscillates periodically in time could in principle exist. So they were these predictions, theoretical predictions, and in condensed matter, in materials, there has been a lot of effort trying to check these predictions. However, because the complication of manipulating the materials and the very fast energy scale, at the moment, there is only indirect evidence of phase 2. Of course, phase 1 is very trivial, but is not direct evidence of this phase 2 and phase 3 oscillations. So the question is if ultracold atoms can help toward this task. And here is when our long-lived multi-level atoms can play a difference. In this case, we are going to put these atoms in an optical cavity. An optical cavity consists of just a set of mirrors where the light can bounce back and forth many times, enhancing the rate at which interact with the atoms. The advantage of these long-lived atoms is that, in contrast to other cases where the excited states decay so fast, in this case, the decay is so slow that we can actively use the excited states that directly couple to the cavity as a qubits or qubits of our system. Let me start by the case when you only use 2 levels, and we are going to elaborate later for multi-levels. So in this case, as you can see that I'm talking here about strontium atoms again. So because the atoms talk between the photons in the cavity, and the photons, imagine that there is one single mode that is propagating back and forth in the cavity. Therefore, the atoms can interact independent on when they are in the cavity. So this is the called Tabitz-Cumming Hamiltonian that describe the atom-light interactions. Here, there is a parameter that is delta C, that is the tuning between the cavity frequency and the atomic transition. A is the operator that creates a photon in this cavity mode. And then this term is just the exchange of excitation between the atoms and photons. Basically, an atom can absorb a photon, and then because it absorbs a photon, it's excited to the excited state, and vice versa, emits a photons and go to the ground state. This Hamiltonian is a simple Hamiltonian, but we want to make it even more simple, and for that, what we want to do is that we are operating in the regime where the detuning is very, very large. So when the detuning is very large, that any other parameters in the system, G, that is this Rabi frequency that tells the rate at which atoms exchange with photons, kappa is the small decay of some decay of the cavity mode outside, some leakage outside the cavity, and gamma is the spontaneous emission that I mentioned that was small in long-lived atoms. So in this far detuned regime, what we can do is that we can actually eliminate what we call is that now the cavity photons are kind of a slave to what the atoms are. And when we do this adiabatic elimination, what we can get is an effective Hamiltonian where, because the photons are so energetically, if I have an atom in the excited state, it can emit a photon, and this photon, before it escapes out of the cavity, is absorbed by the other atom, no matter where the atom is in the array. So the effective Hamiltonian is what is called a collective spin exchange Hamiltonian with a coupling constant that is only set by the parameters of the system, g squared divided by delta. Well, the interesting part is that you can now see some similarities with the BCS Hamiltonian that I was telling you about before. So in a few years back, with my group members, conceived the idea that maybe we can use these atoms in cavities to emulate the behavior of BCS superconductors. We don't have fermions, we can have fermions, but don't need to have fermions. The important part is that you have the cavity-mediated interactions, as long as we identify the position of the atom with the momentum of the Cooper pair. That's the only identification, just changing labels. And in this case, we have this exchange Hamiltonian, and we need to engineer the single particle dispersion. So the single particle dispersion, when you think about the superconductors, one unique feature is that fermions have a Fermi energy. That means that when you have the system very cold, then you occupy all the accessible levels up to the Fermi energy, and then all of the rest is down. Remember that with the mapping, we have pairs of particles. You have a spin up and down, occupying the different energies, low energy levels, and therefore there is pointing up, and the other levels that are high energetically that emptying and pointing down. So you, in this spin, Anderson pseudo-spin formulation, that means that there is a correlation between the sign of epsilon k, that is the energy minus the chemical potential. When it's negative, spins are up. When they're positive, spins are down, and only at the middle, where interaction matters and you have forming the Cooper pairs, you can have some canting that translate into the fact that the atoms of the fermions have not some kind of spin coherences in this language. We love to represent in atomic physics the system in terms of a Bloch sphere, where if the system is atom is in the excited state, you point up. If the atom is in the ground state, you point down. And if you have in a coherent superposition, you point in the middle. And the fully coherent state is when you point along the x direction. So this non-expectation value of the coherences is what tells you the superconductivity. So in order to engineer this type of dispersion, what we decided is that for the qual-atom system, what we have to engineer is the capability to have two separate distribution of spins. And for that, we can really load in the experiment two separate distribution, and we can address them separately. And moreover, we can detune or change the energy of the different parts of the cloud by shining lights to the unexcited state. This is not a big, this is called AC star shift. It's just an idea to modify the energy of the lower energy of the state by just shining lasers. And therefore we can shine the lasers differentially from this cloud and this other cloud. And then we can generate a bimodal distribution that kind of emulates what we need to emulate, that we need to create a BCS ground state. And furthermore, we have the beautiful capability that we can directly measure the order parameter of the superconductor, because atoms emit the light. When the light is a slave to the behavior of the atoms, and when it leaks out, we can detect it, and therefore by measuring the light coming out of the cavity, we really have information about the order parameters of the superconductor. And very nicely, the experiment was done. The experimentalists hear our idea and did the experiment. James Thompson here at GILA, their group decided to follow our prescription and in fact measure the phases of the superconductors. And in fact, we were able for the first time to see all these different dynamical phases. For example, they saw the dynamical transition between phase 1 and phase 2. Remember, in phase 1 is when the order parameter decays very quickly, and in phase 2 is when the order parameter oscillates a little bit and then stabilizes. Of course, we don't have a system that lives forever. We have single particle spontaneous emission. So if we turn it off, for example, in the case of the strongest interactions, we do have a system that lives forever. This is the ideal theory predictions, but of course, that's not what happens in the experiment, they decays. So this is the order parameter as a function of time after a quench of the, in this case, of the single particle dispersion for different values of the interaction. So for the strongest interactions, we go to phase 2. But as we make the interactions weaker and weaker and weaker, the system decays all the way to phase down. The interesting part on the case of metrology is that you can see that by adding interactions into the system, we can push the quantum coherence by almost a factor of 30. So in this plot, I just plot the different interaction strength, and one plot, the blue line, is the lifetime of the system, so how these curves decay, and you can see that when I push the interactions, the ratio between this and this can be of the order of 30, and the other is the average value of the order parameter after some time, that it's finite and then decays. And the decay is at the predicted value of the phase transition. You can see a sharp decay. This is exactly what we see in the theory. So we can claim that we can see phase 1 and phase 2. I mean, similar experiments were done some years ago in the group of Monica Schleider-Mead, but I think here we can really beautifully characterize the transition between the two regimes. Now, but phase 2 is kind of a little bit simple. One of the most excited behaviors is try to see the emergence of phase 3 for the first time. And these were done in the experiment by changing the bias. I mean, remember that I told you that we can engineer the dispersion relation by shining a laser only one cloud and not the other. So by changing the energy splitting between the two different clouds, then we were able to see a transition between phase 2 to phase 3. So by phase 3, you can see this is the experimental line, where as a function of time, as we change, in this case, delta S, we can see that for very small delta S and strong interactions, we go back to phase 2. But as we start to increase delta S and make it stronger, we go to a phase where you can start seeing these permanent oscillations that, in fact, in the experiment you can see, and these oscillations are as a function of this bias in the system. So the advantage is that this allows to give an intuitive picture of the complicated phase 3. So in phase 2, what happens if you have, in this case, remember that we have two types of distribution, spin distributions. In phase 2, we have two initial spins that are pointing out, and then they start each one to disalign or rotate at its own place. But because of the interactions want to lock them and keep spinning and aligning together. But in the other case, interactions are weak, not weak enough, because otherwise all the atoms will completely decohere. That is why it's not phase 1, it's phase 3. Interactions are strong enough, but not so strong to allow each of the clouds precess and have its own trajectory, and beating them back and forth as they come back to the equator, into the x directions of the Bloch sphere. So we were able to actually capture the transition predicted from theory between 2 and 3, not only see as again a phase transition in terms of the oscillation amplitude. This is the experimental points, and the theory, the solid line, also different from the ideal transition, but we were able to see the emergence of the phase 3. And for example, here is the oscillation frequency that is much faster in phase 3, has a minimal the transition point, and is slowed down because the atoms are locked in phase 2. So with this idea story, what I wanted to tell you is that, in fact, there is a way that we can explore the capability to have very different systems to see behaviors that we have not seen before in condensed matter. But now let me move quickly to another paradigm that I find it very exciting. That is the case when we are dominated by dissipation. So let me go back to the regime when the cavity detuning is actually small, but instead, still we have the atom light interactions, but in this case, we have the leakage of the light out of the cavity, kappa, to be strong. So let me go to the regime when kappa is much larger than any other parameters of the system, what we call the bad cavity limit. In this case, we can also write the spin operators in terms of cavity operators. You can see there is a nice symbol here, imaginary sign, imaginary term, because there is a pi half shift when you go from dissipative to not dissipative. But the important part is that dynamics cannot be described by a Hamiltonian, but instead by a jump operator S minus that characterize superradiance. The rate at which superradiance happens is G squared divided by divided by kappa here. Sorry, there is a typo here that I just discovered, but it's related to the cooperativity for the experts, but it doesn't matter. So it's a parameter that determines the rate at which the atoms are decaying because of the collective emission. And maybe you know about superradiant emission, but this is a fascinating phenomenon that was predicted years back by Dicke, and he says that it's a phenomenon that happens because of the collective emission of atoms inducing by when they talk to a common light field. And in fact, for him, is just, according to him, it is when a gas radiates strongly because of coherence between the atoms in the gas. That is called superradiance. So superradiance can be very useful phenomena. And I just wanted to now give you a very simple picture of superradiance. That is a classical picture. I like it because I will going to use this to generalize what I'm seeing here to the case when I have multi-levels. That is the most exciting part of the story. So the idea is that I want to explain you the phenomena of superradiance and connect you to the phenomena of precessions that you can see in a gyroscope on Earth. So for that, imagine that we prepare all the atoms in the excited state, and we are going to let the atoms evolve by emitting light out of the cavity by cavity-mediated interactions. The idea is that the superradiance is nothing that a self-induced precession or oscillations, but in this case, their precession happens in a way that is nonlinear and self-induced. And is set, the precession axis is set through a vector that is perpendicular to orientation of the dipole, the collective dipole of the system. The collective dipole of the system is characterized by the projection of the spin along the XY plane, that is when coherences exist. So basically, the idea is that the atoms are going to rotate and the rotation rate is going to be set by a vector that is perpendicular to the collective dipole, and then is going to evolve in such a way. So let me give you the picture, the cartoon of what happens. If SC is equal to its maximum, there is no projection along the XY plane, so no coherences, but there can be quantum fluctuations, and because of quantum fluctuations, then there could be a tiny dipole induced that is along the Y direction, so the component perpendicular is along the X direction, and then this is going to introduce a rotation. But as you rotate, you can see that you are going to enhance the coherence of the atom, so the rotation rate, because it's set by that, is going to be faster. And then as you increase the projection of the XY plate, you are going to rotate faster, 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 reach the faster rate when you are in the equator, and then just continue and decay. So similar can be seen if you are trying to see the system evolving in a permutational symmetric manifold, when we start all the atoms in the excited state and you emit a photon and go to the permutationally symmetric state with one atom in the ground state, then you have two atoms in the ground state, 3, 4, 4, maximum rate, decay rate when you are in the equator, with half of the atoms are in the ground, half of the atoms are in the excited state, and you go down to the ground state. And in fact, I'm just going to say that this process has been seen in experiments, and this is a very well understood and very nice phenomena. But perhaps the most interesting story is not the idea of superradiance, but when the interference is constructive. But the most exciting story for us is the idea when we have destructive interference. We are going to make the system emit at a much lower rate than you expect from independent particles. So this is called superradiance, and in particular, one special case is the case of dark states, when the atoms do not decay. This is fascinating, and of course, if we can generate these states, these are the holy grail states for metrology, for quantum simulation of quantum information, because the decay rate of the atoms is one of the most important obstacles for retaining coherences. So there has been, of course, intensive efforts trying to actually generate this type of states in ultracold atoms and in superconducting qubits in different systems. The problem is that when you try to do it in free space, it requires the atoms to be very close to each other. And although there has been very great progress in the last couple of years because you can even engineer atoms in a specific type of arrays where you can see the emergence of superradiant tails, still is only very preliminary. And our idea is to change this possibility and facilitate the observation by just taking advantage of the multi-level structure of atoms, long-lived atoms in a cavity. So I'm going to tell you a little bit this work. So, if you can go home and take the story, a punchline of the story that I want to tell you here is the following. If I have two-level atoms in a cavity, I illuminate the cavity with a drive to excite the atoms from the ground to the excited state. Then I wait, let the atoms emit photons from the cavity and decay. There is a superradiant burst, as I showed you before, and then you wait, and all the atoms are going to go to the ground state. This is the well-known superradiant decay. It happens for two-level atoms. It's very interesting, collective emission. If you go to the multi-level and repeat the story, take the atoms illuminated with a drive, and then at short times, you're going to see some superradiant decay. But then if you wait a bit, then you find that at the end, not all the atoms are in the ground state. In fact, there are atoms stuck in dark states. Not only these atoms do not decay anymore from cavity decay, but moreover, excitingly, the atoms are entangled. So this could be the dream of our work. In order to understand this simple behavior, going from two-level to multi-level, I'm just going to need you to add a few elements to the story. So instead of two levels, I have an array of multi-levels in the ground and in the excited state. Now I can only deal with one polarization. We need to do the two different polarizations of the cavity that is propagating along this direction. They have to be orthogonal. I'm going to be careful how to choose the quantization axis. I'm going to choose the quantization axis along the cavity direction to make the treatment easier. And therefore, I have two different types of decay. Through right polarization, when an atom goes from an state in the excited manifold to an state in the ground state manifold, but change the quantum number projection along the cavity direction plus +1, or the other that you can change from -1. So these are two different decay rates, and because we are talking about collective systems and many different levels, the creation and the dipole operator that rules the decay through the right or to the left polarization has to sum over all different possible paths that are allowed in the cavity with a prefactor that is set by the Clebsch-Gordon coefficient, that is set by the atomic structure. And again, we are trying to deal with collective states, so we are not distinguishing independent atoms, but we are talking about a fully collective system. So the story
Sarah, we have about 5 minutes, ma'am.
Oh, 5 minutes. Okay. So the story is going to be very simple now. So now imagine, thank you. So imagine that we have the simplest case that is 6 levels. And in this case, I'm going to try to use a drive that only couples 2 levels, because these other levels are not coupled, because you see that there is not entering the transition. So the idea is that I can choose a basis when I just have a collection of independent 2-level atoms. Of course, they are coupled, but the dipole moment only connects each pairs of atoms. So instead of a one block sphere, I have 2 or many different block spheres, and each of the block sphere can I see a 2-level system. So in this case, what happens is that I'm going to do what I told you before. I'm going to illuminate the atoms with a drive outside from the cavity, and therefore I'm going to rotate each of the sphere by a direction perpendicular to the drive, and each of the block spheres are going to rotate with a rate that is set by the Clebsch-Gordon coefficient of the different transitions. The important story, and this is going to be the home-taking message, is that same story happens to the superradiant case for the case of multi-levels. In here, I have two different block spheres, but the idea is that they're going to behave identically to the case when I drive them, but the only difference is that the rotation axis is a vector that is perpendicular to the collective dipole moment, that is the sum over all the independent spins. So basically, all the atoms are going to behave exactly the same, except all the Bloch spheres that are described by a rotation angle theta that is very similar behavior as when I drive the atoms. And the only difference is there is going to be weighted by the different Clash-Gordon coefficient. So we can introduce the idea of what you call a superradiant potential, where the decay of the particles of the superradiant process is just say like the motion of a classical particle with instead of angle position theta that is subject to a very dissipative potential. So very basically, if I can write the potential of describe the behavior of the atoms as a function of some angle, and you can see, and this is the idea of the superradiant decay, that if I prepare my atom in one direction and then I let it evolve, the atoms is going to go to the right if the slope is positive, and then be stuck at this place. And it's stuck because not individual dipole moments are finite, but because the sum can be zero. And also the same case, if I'm here and let the system decay, it's going to be stuck in the ground state. And therefore, I have these points where the system is are steady states. Some of them are stable, some of them are unstable. But the idea is the ground states is where we have these mean field dark states. So these mean field dark states are states where the system gets stuck, doesn't decay, even though I predicted this by a very simple mean field picture. If I try to do quantum calculations that we can do for this permutational symmetric system that I come for quantum fluctuations, I indeed see that as I increase the particle number, all the particles that start from the right of this maximum are going to decay to zero. All the other, when in this region, I'm going to decay and get stuck in an excited state, creating dark states. And then I'm going to go down, I'm going to decay back to zero. This is very exciting. So then let me tell you that, well, what was something that we wanted to characterize. My computer got stuck precisely when I wanted to say something. Let's see. Jesus. Restart the program, maybe. I'm going to restart my PowerPoint. I'm so sorry. Okay. Okay, let me, hopefully you are seeing my screen. Are you seeing my screen?
Yes, we're seeing your screen.
Okay, yeah. So, I'm so sorry. I don't know what happened. So I'm just going to make my story short. And just wanted to tell you the story about entanglement. So the idea is that we can characterize the system and we can show that these states not only are dark, but are highly entangled. So we can do simulations including all the quantum states. And the idea is that if we put ourselves in a state that are supposed to be mean field entangled, but we let it evolve under the full quantum effects, of course, it's not the exact solution, but still what I'm trying to show here is that still is very close to the quantum solution. So the steady states are entangled, they're dark, but the entanglement is very little because I increase the particle number, they get less entanglement. As you can see, as I increase N, the mean field state is almost the same as the dark state, the full quantum state. So the story is that for atomic clocks, we want to entangle the particles because if we have an entangled state, we can actually measure better. And this is a holy grail for metrology. And we want to characterize the degree of entanglement is through what is called a spin squeezing parameter. That is the ratio of the variance of my noise distribution compared to the one that I have from a coherent state. In a coherent state, the noise distribution is very simple. It's a circle. Here is a ellipse, and therefore the decrease in not only in the noise not only tell me the better metrology capabilities, but also tell me the possibility to actually it's a witness of entanglement. So the story that I'm going to tell you now, I know that I'm running out of time, but is that if in addition I have my cavity system, but I drive it before I let the atoms excite the atoms and let it evolve and then they decay. But now, if I in additional keep my drive on, I can generate states that are entangled. So I have the superradiant potential and I keep my drive on and I want to look at the steady state. And the idea is that if I have a steady state, I have two different regimes. When the drive is smaller than the dissipation, then I can get a steady state where the atoms are going to reach a finite state that is pointing in some place in the sphere. But if I drive too strongly, then the drive is going to be too fast and the atoms are not going to keep rotating and never going to equilibrate. But in the middle, there is going to be a transition that is called the decay transition that is characterized at the inflection points of the superradiant potential. And at this steady state, even in the two-level system, you can generate a squeezing that is useful for metrology. So the story that I want to tell you is that unfortunately, if we have these states and for the two-level atoms, and I stop driving the atoms, the entanglement is going to be disappear because all the atoms are going to go to the ground state. What we have discovered is that in the multi-level atoms, I'm not only going to be able to generate these dark states by operating at specific points of the superradiant potential, I can have states that are critical. That is when the second derivative of the superradiant potential is zero, but also the first derivative. So there are states where there are points in the superradiant potential where we are going to have a squeezing that is scalable when we have states that are dark and highly entangled and useful for metrology. We will have not only one squeeze state, but many squeeze states. So the idea is that we have this type of very highly entangled state that are dark and critical. So I'm going to skip the details here. But the important part that I want to tell you is that these ideas, we are going to apply them for state-of-the-art optical clocks. This is the plot of the fraction frequency uncertainty versus year. And we can see that lately the optical lattice clock are reaching record levels of sensitivity and accuracy. Basically, we're building a clocks that never lose or gain a second in roughly 15 billion years. That is the age of the universe. This is by using these strontium atoms. And now we are placing them in an optical cavity. So this opens fascinating opportunities because not only by controlling many atoms, we are able to actually gain a signal to noise. We have been able, in collaboration with the strontium group, to actually understand a little bit the role of collisions that are playing an important role because atoms and fermions, therefore they collide. And the idea is that even though they collide weakly because of quantum statistics, still collisions can make a fundamental role in this system. So they collide weakly, but still they collide. And the idea is that by trying to control these collisions, we were able to actually, by controlling these collisions and making gravity an important part of the story, we were able to operate at points, depending on how we hold the atoms, at conditions where we can have the collisions completely suppressed, that is called the magic depth. And by operating at this point, we were able to suppress any undesirable collisions, and they're able to cancel any systematic, and we're able to first time observe a prediction made by Einstein that he said that clocks at different height can have different ticking rates. So by understanding the properties of this clock, we were able to actually measure this different ticking rate that can be at the level of 10 to the minus 19 at 1 millimeter apart. This was measured before at NIST when the ions were separated at 30 centimeters apart. But in this case, we were able, with the collaboration with Jun's group, measure this gravitational density shift by controlling the collisions of the atoms. And in a measurements of 10 days, they were able to resolve the different ticking rate of two parts of the clouds that are separated at 1 millimeter distance, and they were able to measure a gravitational redshift that is as low as 10 to the minus 19, but is consistent with the rate of the acceleration in Earth. So with that, that was accomplished in nature. So the next story is that we want to combine the entanglement that I was just telling you that naturally appears we have the atoms in the cavity, and hopefully we were all using these dark states, not only for quantum simulations, but also for metrology. And hopefully we combine all these ideas of multi-level atoms in cavities. We can tune the interactions and for the first time explore, for example, the competition between many body interactions and gravity, and answer questions about the universe that we don't know yet. And with that, let me just finish by thanking my team members that has been very important in the description of the models that I show you. Of course, collaboration with the experimental group, all the cavity QED measurements were done in the collaboration with the group of James Thompson. And also we have done very nice collaboration with the clock experiments with John G. And the idea is to combine the efforts of these three groups to hopefully lead to directions that we have not been able to do before. And of course, the impressive and the very useful support from the Air Force that has been able to allowed all this very nice investigation, and hopefully we will continue doing exciting new physics. And with that, thank you for your attention, and sorry, I think I was a little bit late.
Thank you, Professor Rey. We do have a little bit of time for some questions, and there's already one in the Q&A from Lucia Medina, who asks, what made you want to study this topic?
So the topic of, let me try to read the question. You mean the topic of ultracold atoms or the cavity of cavity QED systems? Well, I mean, for me, the idea of trying to use fully controllable systems for something that is useful in the sense that we can show that quantum mechanics can lead to advances that would not be possible without quantum effects is fascinating. So the idea of building the most precise atomic clocks or timekeepers that we have ever imagined by taking advantage of the atomic structure of the atoms is just fascinating. And I mean, we have built very, very precise atomic clocks, but I think the excitement is about to come because these clocks are still classical. So my role has been always trying to come up with theoretical methods so we can take advantage of interactions between atoms and light and atoms themselves and try to push the metrology to levels that we have not imagined before, and hopefully can lead not only to important fundamental advances, like, for example, we measure the GR shift in a millimeter scale sample. What about now we combine it with entanglement, and we can see for the first time how gravity and entanglement comes into play by just controlling these very pristine atomic systems. I don't know if this is was a good answer or not, but I'm happy to discuss a little bit more focus if that was, I mean, depending of the question.
I think that was an excellent answer. Oh, and in the chat, she says, yes, she was referring to your interest in atomic clocks and systems and multi-level long-lived qubit states.
Okay.
Absolutely. Excellent. Well, I know we have a couple more questions that have come in, but we have run out of time for our lecture today. And so I want to take a moment to thank our speaker again, Professor Rey. Thank you so much for this really insightful talk. We will take the questions that have been put into the Q&A that we did not get to and try to potentially try to answer them offline since we have the details of everybody who registered for the conference or for the lecture today. I want to thank Dr. Grace Metcalf for inviting our speaker today and introducing her, and thank everybody in our speaker today for joining us. And I look forward to seeing everybody again in our next Chief Scientist Distinguished Lecture Series talk next month. Thank you very much.
Thank you. Thank you very much. Bye-bye.
Thank you all, and I'll be closing the session now. Thank you so much.